Denuvo. Fine. Denuvo is an infamous DRM solution used in games. Technically it is a DRM for DRMs, the idea being a developer would use it to protect other DRM solutions like Steam or Origin, providing a defense in depth with sophisticated anti-tamper techniques. Let's set some expectations up early. This will not be a full crack. The game in question will not run. However, we will uncover all the tricks this particular version of Denuvo uses and write a crack that bypasses the initial checks. I'll get into what this actually means later, but essentially we'll be solving the fun part, and then everything after that will just be grinding out more of the same. This video is the culmination of 3 months worth of work, the largest project I've ever worked on. Normally when I look at DRM, I try not to look too much at prior art, as the fun is in the discovery. However, for this I did do a lot of research as part of it, and I'll link all the resources down below. So what game was the subject of my 3 months of misery? The classic Formula 1 2016.
Welcome to Formula 1.
I chose this game for several reasons. It's an unlisted game, so there's no impact to sales. There's already a crack for it, so I'm not changing the status quo, and it uses an early version of Denuvo. On that last point, it means that nothing I do will affect modern games. The techniques I show here have all been fixed on modern versions of Denuvo, but the fundamentals of how it works remains largely the same. Also, looking at early versions makes it easier for me. Not easy, just easier. Okay, there's a lot to get through, so let's start with how Denuvo works and what our end goal is. The fundamental technique Denuvo uses is well known. In fact, it's in the original patent. When you want to protect a function with Denuvo, it selects certain constants from the assembly. It then takes these out of the code and stores them on the Denuvo servers. When the game starts, it collects a bunch of information about the hardware it's on, the hardware IDs. These are then sent to the server. The server takes the constants of the game you're running and encrypts them with a key derived from the hardware IDs. It sends this blob of encrypted constants back to your machine, and this is known as the token file. At runtime, the game will decrypt the constants using the hardware IDs. The idea being that if you've copied the game and token file to a different machine, then the constants will decrypt to different values, due to the hardware being different. At this point, the game will likely crash. This diagram certainly clears things up. But what happens if you make a legitimate change to your hardware? Well, there's a provision made for this at the start of the game. Denuvo will do a check against all the hardware IDs and see if they match the token file. If not, then it will delete the token file and request a new one. And it is this check that is the focus of our project. If we can bypass this check, then we know we've identified all the hardware IDs the game uses. The game itself will have many checks, but they will all be based on those initial checks. So the game is to identify what information Denuvo wants and feed it to that so it thinks the token file is valid for the current machine, even though we'll generate the token file on a different PC. Of course, it's not as simple as that. Denuvo has a bunch of anti-tamper checks that prevent us from easily patching the code. There's 3 components to this project. 1, the Denuvo hardware ID checks, which actually check the machine is associated with the token. 2, the anti-tamper checks, which continually verify if the code has been tampered with. And 3, the virtualization layer, which obfuscates all the code. We'll need to dive through and handle each of those layers in order to influence the game as it's running. We can use a tool called Detect It Easy to get some information about the game. We can see here it's using Denuvo version 2 with Steam, and the S-data section of the binary is packed, i.e. obfuscated. So given just this information, we can make some inferences. The first is that the S-data section is probably going to contain the important code we want as it's protected. In fact, looking at it in Ghidra, we can see that the rest of it is just garbage. The second takeaway requires a bit of research on Denuvo, but it's quite easy to find out that games with this version use another third-party tool called VM Protect, or VMP, to obfuscate their code. Future versions of Denuvo replace this with their own custom virtualization layer. But what is virtualization, and what misery does it entail for us? Essentially, virtualization is a technique to obfuscate what code does. You start by defining an architecture for a custom CPU, complete with a custom instruction set. Usually this is a stack-based RISC architecture, but the details can be as ambitious as you want. Next, you build up tooling that takes a regular function in your compiled game, in x86 assembly, and transpiles that to your virtual architecture. You then embed into the game an interpreter that will convert the custom architecture into native code. Finally, you rewire everything so that your original function is replaced and instead runs through the VM. This is a pain to reverse engineer, as you have to fully reverse the custom architecture as well as the virtual machine implementation before you can even start to understand what the purpose of a function is. So let's do that. Actually, before we do that, we have a minor side quest to embark on, the packed sdata section where all our VMP code is going to reside. I have neither the time nor the patience to figure out how this is packed, so I've just run the game and dumped it after it's finished unpacking. This gives me enough of the binary to load into Ghidra so I can start looking around. The version of VMP used is VMP2, and to be clear, I've not reversed this myself. The back engineering group have done that and written up quite a detailed explanation on it, as well as some tooling. However, for my own understanding, I did ignore their tooling and build my own. This kind of DRM analysis is all about building custom tooling, so let's go through all that. The VMP2 virtual machine is quite simple. It has a virtual instruction pointer, which is always the native register RSI. It has a virtual stack pointer, which is always the native register RBP. And it has some virtual registers, which are always an offset from the native register RDI. Then there are a bunch of instructions the VM can execute. I won't enumerate them all, but they're what you would probably expect. Reading from memory, writing to memory, maths operations, and calling functions. As I mentioned before, this is all stack-based. If we look at the add instruction, we see it adds two values together on the virtual stack and writes the result back to the virtual stack. The Denuvo code will largely be executed via this VM, so we need to start to break it down and build some tooling around it. There are three components to this machinery we need to find to recover a protected function. The handlers, these are the native assembly instructions which execute the virtual opcodes. The handler table, an array of all the handlers needed for a specific run through the VM. The VM instructions, these define the execution through the VM and consist of an index into the handler table and optional arguments. At a high level, when a VMP2 protected function is executed, it will save off all the registers, then set up the VM state, which includes resolving virtual instruction pointer from a constant push to the native stack and points to the virtual instructions. It will then progress through the instructions, executing handlers until the function logic is complete. At this point, it will then restore all the native registers. Sounds like a lot? Well, as an added bonus, the table and the instructions are encrypted and all the handlers are obfuscated. Let's keep breaking this down. There's a special opcode called VM entry that all protected functions execute first. This saves off the native registers and sets up the VM, which includes loading the address of the handler table. It does this with the load effective address R12 native instruction, which is quite easy to search for. So this gives us all the VM entry handlers in the binary as well as the handler tables. However, things start getting tricky here. We can't just manually read through the assembly to find the rest of the code, as VMP employs two irritating obfuscation techniques. The first, and most obvious from looking at it, is the jump obfuscation. Basically, VMP has taken all their functions, split it up into small chunks, and stitched them together with jump instructions. This means you cannot see a linear progression of the code, and it completely breaks Ghidra's decompiler. As an added annoyance, these jumps interleave with other obfuscated functions, so all the code is just one blob of jumps. Also, some of these jumps are conditional and have duplicates, so there's multiple paths through the obfuscated code. The next technique is dead store obfuscation. This just adds loads of junk instructions between the legit ones. They're all valid x86 instructions, so won't cause a crash if executed, but they change state unused by the VM. Effectively, they add a lot of noise to the analysis. We can heuristically remove both of these. I've created a basic app that can read in the game and pass out the sections and provides a good starting point. First of all, we use libcapstone, a disassembly library, to pass out the instructions the game is executing. From there, we can emulate the code by stepping through each instruction. Despite there being multiple paths through the code, all roads lead to Rome, so we just follow the jumps and record the instructions between them. This will then give us a flattened path through the code. For the dead store obfuscation, we mark each instruction as whether it is a read or write to its register argument. We then walk forward until we find another usage of that register. We only care about the last write in this chain before a read. Any other writes are dead stores and can be removed. By applying this heuristic over and over, we can slowly remove the instructions that don't affect the final execution, and we're left with something like this. Okay, so we can find the array of handlers, but the table is encrypted. The encryption isn't too difficult to revert. In our cleaned up VM entry code, if we look forward from where it loads the handler table, it will eventually load the first index to execute into either RCX or RDX with this instruction. From here we walk forward again until there's another operation on that register, which is the decryption operation. Luckily in this case the decryption is just done with a single instruction, so I've knocked up all these in the code. They're simple things like XOR, NOT, byte rotate, etc. As the same operation is applied to every entry, we can now fully recover the table. Okay, so now we know the address of all the handlers in the binary, but we don't know what those handlers do. Now comes the real grind. The article details the native instructions each handler uses, which, since we've cleaned up the handlers, we can easily pattern match against. So I spent some time and added pattern matches for all the handlers, including a couple that weren't mentioned in the article. A bit more forward engineering and tidying up, and we can dump all the handlers to a JSON file. If we want to understand what these are actually doing, we really need to be able to emulate the VM. Conceptually, this isn't too complex. Just implement all the opcodes and set up a stack and some virtual registers. However, as always, the devil is in the detail. The virtual instructions can be located by looking for the first real instruction in the VM entry which pushes the address of the instructions to the stack. Obviously this is encrypted, but VMP2 uses 3 of the same encryption primitives we saw earlier, so it's easy enough to decrypt. The problem now is figuring out which opcodes are executed. Although we have the address to the instructions, the individual instructions are themselves encrypted. And it's not just a simple transformation this time, it's a rolling encryption, meaning the result of decrypting each instruction feeds into the decryption of the next. Couple this with the fact that the virtual instruction pointer can move both forward and backwards, and we have an all or nothing situation. We need to be able to fully emulate the VM in order to get all the opcodes, and there are 20 handler tables in the game. I started building out this emulator, but it was a lot of work. I was a month into this project and I hadn't even gotten to the Denuvo bit yet. However, there's a key observation that allows me to break through the VMP2 and continue making progress. The VMP2 instruction set is, by design, quite limited, which means there's certain operations that cannot be executed in the VM. There's a great blog post by a chap called Connor which covers the high-level details of Denuvo, including some of the known hardware IDs. One of the most iconic ones is the x86 instruction CPU ID. This instruction returns various bits of information about the CPU and is hard-coded in the silicon, so hard to spoof. But the VM doesn't have a CPU ID opcode, so it has to do a full VM exit before executing this instruction. So we can use this info we found so far to find some of these. This is a good starting point, however Denuvo has more tricks up its sleeve, so we know it won't be this easy. We need to start exerting some control over the game, and the easiest way to do that is with DLL hijacking. Basically, we can look at all the libraries the game loads at startup and find one which doesn't expose a lot of functions. We can then write our own library with the same name and exports and drop that into the game directory. A nice property of Windows is that it will find our library and load it first before it starts looking in the system files. So I've created a new dinput8.dll and made it the same shape as the real one. If we add a special function called DLL main, then Windows will also execute this when it loads the library. So if we add some simple login code, we can see we get loaded and executed. The nice thing about this technique is that our code gets executed right at the start of the executable's lifetime, so we can use DLL main to do some interesting things before the Denuvo code is even run. We'll need to hook some native Windows functions, and the easiest way to do that is with the import address table, or IAT. This is an array of function pointers where each entry is the actual address of an imported function. So doing some Windows PE parsing, we can resolve the offsets into each function and overwrite that with a pointer to our custom function. If we make the hooked function the same shape as the original and keep a copy of the original, then we can create a simple hooking framework. There's one more bit of machinery we need to set up, a vectored exception handler, or VEH. In Windows land, all exceptions are handled by the kernel, and this includes access violations and other low-level errors. The thing is though, Windows allows us to register a custom handler for these, so we can provide custom handler or recovery logic when they occur. It gives us incredibly powerful access over the executable. We can even change the values in the registers before optionally continuing execution. Okay, let's take a look at some of the CPU ID instructions we already found. As CPU ID will give a different value per machine, we want to make it such that it will always give a consistent value, and the easiest way to do that is with patching. We could overwrite the instruction with a jump to some custom code, but a CPU ID instruction is only 2 bytes, and a jump will be more than that, so we'd have to save off the overwritten bytes and do some bookkeeping. In this case, it's much easier to overwrite the CPU ID instruction with the UD2 instruction. This is a special 2-byte undefined instruction which will always generate an invalid opcode error. On Windows, this will get raised as an exception, which we can then write a custom handler for. In our handler, we can update the instruction pointer to any code we want and get Windows to resume the application, therefore redirecting execution to our own code. Sadly, in Denuvo land, things are rarely this straightforward. If we try doing this, then the game crashes. What Denuvo is doing under the hood is monitoring its own code, constantly calculating CRCs to see if it's been patched. If it detects a patch, it dies. Now, your first instinct might be to reverse engineer the CRC checks in order to be able to bypass them. However, this is not a trivial task. The checksums being calculated will be complicated and be executed via VMP. There is, however, another way. At the lowest level, pages of memory have a protection level that is enforced by the CPU. A page can be readable, writable, or executable, or some combination of the three. If you try and read from a non-readable page, then the CPU will raise an error that we can handle with our VEH. So normally code will be readable and executable, which makes sense as this allows the code to run, but also the code to read itself to calculate the checksums. Now we can change the protection of a page in Windows with a function called virtual protect. So if we change the protection from read executable to read only, then when it is executed, we can capture the access violation exception. At the start of our library in DLL main, we can copy over all the code into a shadow section, which we are free to modify as we want. Then we mark the page the CPU ID is in as read only. When the game tries to actually run the code, our handler will be called. We can then change the instruction pointer to redirect execution to our shadow section, which will have all the CPU ID patches already in place. In essence, reads will happen as they always have from the real code, but execution will be silently redirected to the shadow code, where we can make whatever changes we want. Of course, this doesn't work. Even after wiring up all this boilerplate, the access violation is never triggered, which means we never redirect to the shadow code. By hooking and logging virtual protect, we can see that the game continuously resets the protection of the pages it cares about, thereby undoing our little trick. So we need to add some logic to our hooked virtual protect, which prevents the pages from changing whilst reporting to the legit calling code that it was changed. The same goes for virtual query, which the game can use to check for the current protection level of any page. And this works nicely. We can see the access violation and then our hooks being called. I've kept using the UD2 trick for patching for simplicity, although it does have a performance overhead. We now need to find all the CPU ID instructions. Spoiler alert, there's more than just these that happen on VM exit. Let's talk about pin. Pin is a tool by Intel for dynamic binary instrumentation. It enables the injection of arbitrary code into an executable via a custom JIT engine. It hijacks the instruction pointer, saves register state, and translates the program's binary code into a new stream of instructions on the fly. As it's fully programmable, we can do interesting things like log specific instructions like executed, say CPU ID. In line with the universal truth that as software gets more complicated, it gets more complicated to build, I bashed my head against their limited instructions for several hours to build a custom plugin. And we can trace CPU ID instruction execution. Pay close attention to ones like this. The address is very interesting as it's not from the game code, but a heap allocation. If we wrangle our debugger, we can see that this gets reified as this. So somewhere in the bowels of Denuvo, probably via VMP, it's jitting custom CPU ID checks. Great. Pages of memory can be allocated with virtual alloc, so by hooking this and carefully logging, we can work out that all the jitted code comes from this massive allocation here. One of the arguments for virtual alloc specifies the protection, so in our hook, we can wait for this large allocation and then silently switch out the protection for read-only. Then we can cache execution of this region with our VEH. Of course, we can't know when the jitted code gets emitted, so we just wait for the game to try and execute it, and then we recreate the new shadow region with CPU ID patches every time. We also need to make sure the game doesn't try and change the protection back. Small side quest now, but we need to create some machinery to capture the hardware IDs when run on another machine. This is just a struct with the data we want to store. When the library is loaded, it checks for the presence of a hardware IDs file. If it's not there, then it enters record mode, fills out that struct, writes it to a file, and then continues. If the file is there, then it enters replay mode and fills that struct from the file before continuing. If we replay the CPU IDs from another machine, then we get this pop-up. As I said in the beginning, there is already a crack for this game, however it works differently to what we're doing. Instead of patching out the hardware ID checks, it instead generates a legit token file for the current machine, so we can leverage that for testing. Let's copy the Denuvo token file over from another machine. If we try and run the game, we get this pop-up. This means that the initial checks have failed and the game wants a new token file. In fact, it even deletes the old one. As a reminder, our goal is not to get to the game, but to get past this pop-up. Replaying our CPU ID values from the other machine, we still get the pop-up. This means that there are other checks going on. The fun thing about Denuvo is that it's an all or nothing solution. We either get all the hardware IDs, or we fail. The next thing Denuvo does is read data from the headers of system DLLs. This makes sense as they will be subtly different between each version of Windows and can therefore be used as a way of identifying the system. Parsing the pin and my own logs, it looks like all the reads happen with the VMP2 read DW opcode. So again, We can mark that page with that instruction as read-only and catch it with our VEH. The opcode just dereferences RAX and stores it in EAX. So in our handler, if we detect that RAX points into the headers of a system DLL, then we emulate the read by setting EAX to the corresponding value in the data captured from the other PC. Again, by carefully logging the reads, we can see that it reads from ntdll.dll, kernel32.dll, and kernelbase.dll. Still pop up. The next check is kuser shared data. This is a largely undocumented page that gets mapped into all processes by Windows. It contains data the kernel wants to share with the userland process to facilitate fast access. A fun Windows fact is it's always at this fixed address in every process. It does contain some fields that can be used to identify the system, including the NT version and processor features. kuser is read-only in userland, so we can't just change the values to match that of another machine. Instead, we need to do the same song and dance we've done before, find the read instructions via vmp2, mark them as read-only, hoover up the kuser data from the other machine, and emulate the code reading from that. Still pop up. Hopefully, the final check in this version of Denuvo is the Process Environment Block, or PEB. This is a special structure that the Windows kernel creates for every process. It contains a bunch of useful information, including the OS version and number of processors. Luckily for us, you can easily get a pointer to the PEB using this compiler intrinsic, and as an added bonus, it's writable. So we can just capture that data from the other machine and squirt it straight into our own PEB. Even after all this machinery, it's not working. In fact, it's crashing before the pop-up. The problem we have is that all this VAH shenanigans has introduced some overhead into the code execution, which Denuvo is detecting. It'll be running periodic timing checks to see how long its own code takes to execute. If it takes too long, that's indicative of either excessive hooking or a debugger being attached, two things Denuvo doesn't want. So we can amend our pin tool to also find RDTSC instructions. This is an x86 instruction to get the current processor time. If we apply the same hooking technique as before, then we can force the return value to be a consistent small delta rather than the actual value. The other issue we have is that Denuvo registers its own VEH, which interferes with ours. The fix is quite simple. Hook the Windows function for registering handlers and make sure theirs gets inserted into the handler chain after ours. That way we get first refusal of all exceptions. Okay, so after all this, and some bug fixes, we can finally not see the pop-up. How anticlimactic. 3 months of late nights, long hours and frustrating work to not see a pop-up. We're now in the main Denuvo checks, which are designed to crash when the hardware IDs are incorrect, rather than display a friendly pop-up. The thing is that this video was not meant to be a full crack. It was to explore the mechanics of Denuvo and some of the techniques used to bypass it. If we wanted to do a full crack, we would just need to grind out and patch all the checks, which is more of just the same. However, a core part of Denuvo is randomness, so it could easily take another 3 months with pin to find them all. I'll link the resources I used for this project in the description, but I just want to say a huge thank you to Carl, who helped keep me sane during all this. I sent a lot of random hex addresses to him in the early hours of the morning with mixed feelings of hope and anger. He also helped me out with the pin tooling. We have a Discord. If you want to hang out with people who find this kind of thing interesting, then feel free to join us. That being said, the low-level fun doesn't end here. If you want to see how I hacked a Unity game, then check out this next video.